Okay, so if you put the closing parenthesis there, it should work. Yeah, remove the comment and then put the parentheses. And go ahead and run it and see what happens. We've got TF text.
Oh, okay.
And double click on it, make sure that it's. So it's not organized very nicely, but it's there and it does contain the information.
Okay, thank you so much. Yeah. Wait. No, it's good. See, piece one. When I say people or say you? Because I think he is very good for the one that we can see in the line together. Yeah, you know, it's go. Sorry. One say if you make a new one. And you have it say, oh, I think it was if you did save. If you typed in save. Data. Oh, see. But it was this one. Right, I think I'll save them. I'll try that. Maybe three. And then it should be there. And so if you were to do instead of a CLC, you know, it's CLC settings and clear. With the key one, again, if you put welcome. Yeah, good no. Oh, thanks. We just use the Dropbox. Right. Yeah, it's very nice. Let me see. It's more easier to. Okay. So. That's. And then you can open it from. Yeah. Because you're signed in to it now. Yeah. I'm using the school. I think it's providing support. Really? I know for sure they do. I can maybe. You have the rest figured out? Yeah. Thank you. You're welcome. Thank you. In a reference and then I'll just text me and I'll see if maybe I can work on for.
For like computer engineering. There, like, wait. Did you use like legend?
I did, but it didn't tell you you needed to.
Yeah,
I
like
think
the,
it's fine.
or whatever. I didn't use.
No, I think you're good. I think he said, starting today, he was saying. If you have a graph, you should probably put one in, so maybe in the future time. But I think it's gonna be the first time. He didn't say.
Yeah, those Costco pizzas are like this. Gross. Six. No. I'll very good.
Isn't it three conditions for number one? Less than zero?
No, so it's the first derivative and second derivative. That's what I'm referring to.
Oh, okay.
But yeah, the second derivative, there's three cases for that, but yeah, first derivative, second derivative.
I don't remember the direction.
Sure. Yeah, absolutely. Yeah.
So then, what's, am I doing this, or is like, okay, my number was 20. Obviously, we start with 50. He says 90, so you know, part of 70, closer to the beach.
Yep. Yep.
Is that just like that?
Yep.
Okay.
Yeah.
Yeah.
There's,
I felt
yeah,
that was like-
it's not in
So-
order of like, more information. There's some algorithms that work better than others.
Yeah.
Yeah, so we'll illustrate that kind of later on. Yeah, that's basically.
Well, we figured that out. We could do subtract.
Okay, in my defense, somebody just randomly Googled.
So I guess.
Okay, yeah. There's different strategies with like starting guesses and things like that.
Yeah.
They get really interesting. It looks cool. I had another problem there before, for signing, but I wanted to kind of get this one in first, so, yeah.
Yeah, it's simple, but I mean, it's made any points.
Yeah.
Or some public street, I'm sure, not the public one.
Okay, the very last one, my graphing calculator, like, I don't know if I input everything wrong. Cause I did everything like was on the first two portions of number 4. And I put in like the constraints and then it just didn't display anything.
No, like, which mine was like first was not, that didn't work. And then, somebody recommended the social spreadsheets, I got the first two, but then. Took out all the constraints right, I have the answers for the functions, but then they gave me a,
I don't know.
and I'm like.
What I was doing was I just used
Literally.
the Desmos graphing calculator. Have you used that?
It's been a while.
I went through it and I like put in the constraints specifically afterward and it didn't even graph anything for this one. But on the others, it would work fine and I would just be like, okay, here's the. So the other ones that worked.
No, you can.
And then for this one, it like didn't graph it. I don't know if there was something else I was supposed to do. Cause then I made it like f of x of y and I was going on like Google, like the questions on how to do it. And this looked right. And I'm like, I don't know why it's wrong.
But
So I had most of it and then just that last question, like I spent a long while trying to figure it out and I didn't. And I was just like, have most of the homework.
I did the first one, column 2, I don't have it.
One of the big like math.
And then-
So long.
Yeah.
And then like, yeah.
Oh, my problem 3 was also. And then. So he gives you the answer and I would just like pick a different point and be like, hey, this is also. So it doesn't look like I'm just copying it.
No, that's what I was talking about. I didn't realize the answers.
Oh, yeah, he gives you.
I was like,
Yeah.
oh.
So you kind of know, and I would just pick like this random point that is like, okay, this is also inside.
No, I was just like, oh, I guess I'm just following the instructions, and then all of a sudden I just like A and X, and I'm like,
Yes.
so yeah.
So I did have everything except for the last question. I don't like.
So I don't.
I mean, looking at what it's supposed to be makes sense.
4 years.
And it's supposed to, it just didn't graph for me.
Yeah.
I couldn't figure out.
No, same. Like again, I just have one line. I don't have. It's like, well, look at it. It's like right a quarter.
But that last one was the first, that was a function of two variables, so maybe I like somehow put it in wrong and didn't understand what I.
What I was doing. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Surviving? Yes, everyone survived the heat wave. That's good. Yeah, it's been crazy. Oh, I think tomorrow is supposed to cool down a bit. Today feels a little bit cooler too, so yeah, hopefully it's better. Yeah, okay, so I'll admit, today I might be a little bit out of it today. So yesterday we kind of had that social event and I drank a lot of soda. Soda is my vice, and so I drank a lot of soda. I was really hyped up. I couldn't really go to sleep. So this morning I was okay this morning. I got through my work okay. I was crashing kind of early afternoon, so I did the really smart thing was drink another soda to try to get me through the afternoon. So it got me through the afternoon, but now I'm like crashing. So I might be a little bit out of it today, but you know, I think, yeah.
Okay.
Yeah. But now that I'm talking, I feel a little bit better, but you know, it's like it's kind of coming in waves today. So yeah, but hopefully it'll be okay. Okay, so today the plan is we're going to finish up our lecture on unconstrained classical optimization, and so I think we had just a little bit of the example that we started last time. We'll finish that up today, and then we'll get to multivariable optimization. Okay. All right. So announcements. Member homework 1, I think is due pretty soon. I believe it's due. When is that due? That is due tonight. So, so make sure you guys get that in. I think for the most part, you know, everything in the homework, there's no calculations on the homework. It's just, you know, one of the questions is just a game, and the rest is just kind of interpreting graphs, drawing graphs, and so you know, just kind of make sure you get that in. If you have questions on the homework, I know I had to cancel office hours yesterday, but I will be pretty available tonight. I might drink another soda, so I might be pretty hyped up tonight. So you know, if you send me an email later tonight, I might be a way to answer it. Okay, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. First thing I'm gonna do, let's go back to the lecture notes from last time. Actually, let me do a recap first. I think that might be a little bit. Okay, so right now we're kind of right in the middle of what I kind of call classical optimization. We're not going to spend too much time here. We're really kind of only spending the first third of the class. Because if you remember, you know, classical optimization, this is how people optimize functions before the age of computers and all that good stuff, right? So this is kind of you're kind of witnessing kind of the roots or the kind of the origins of optimization. And so what makes classical optimization unique is that it's really kind of the only method that you can kind of practically do with the pencil and paper. And there's kind of two conditions that we said that, you know, in order to find optimal values using this method. So oftentimes, you know, the classical methods are often referred to as derivative-based methods because, you know, everything that we're doing here relies on derivatives. Okay. So the first condition we had was to take the first derivative of the objective function. And then what we're going to do at that point is set that equal to 0. We're going to take, you know, let's say, you know, generally the variable that we use for objective functions f and we're optimizing a variable x, since we take df dx is equal to 0. And so by solving for the values of x that satisfy this equation, that gives us the locations of we call them the extrema. And so by extrema, for the most part, those are either going to be, minimas or maximas in the function. But there are another possibilities that those points could be saddle points. Okay. And so remember, a saddle point is neither a max nor a min. So technically it's not an extrema, but I just use the term extrema just because it's longer to write max min saddle point. All right. And so the second step, or the second condition that we had to determine, was to characterize these extrema as a max, a min, or saddle. And to do that, we had to take higher order derivatives. Most of the time, just taking the second order derivative is going to be enough in most cases, but sometimes you have to go further. Okay. Right, and so what we're going to do once we compute the higher order derivatives is we're going to evaluate them at the locations of the extrema. So we're going to plug in all of our answers from part 1, and then depending on the sign, that's going to tell us, whether it's a max, a min, or a saddle. Okay. And the exact conditions for this, it's a little bit complicated. So if you remember from last time, it depends on the order of the derivative. And so if the derivative order was even, positive or negative, then that tells us certain things, or if it's an odd order derivative. So definitely look back in your notes. I'm not going to write that whole thing again just because it takes a while, but generally this is kind of what we're going to do, right? The classical methods are derivative-based methods. So we're going to take derivatives. What we're going to be doing today, for the most part, is we're going to be taking these two conditions and seeing how they kind of generalize to multivariable situations. Okay, because everything we've been doing up to this point has just been single variable, so we're just taking simple derivatives. But when you have multiple variables, 2, 3, we're not going to go beyond 3. There's you'll see that these steps are kind of just generalized very clean. Okay. So that's mostly what we covered on last Thursday. So let me jump back to the example that we're doing. Just because we just had a little bit more, and I don't want to leave you hanging on it. Okay. And so just to kind of remind you of what we were doing, we were optimizing this two-stage compressor. Okay. And so the idea is that gas is going to go through this system. It's going to compress to a certain pressure. And what we wanted to do was we wanted to optimize the cooling pressure, P2, to minimize the amount of work or minimize the amount of energy that's required through this process. Okay, this is a very common thing. So anytime you're running kind of an energy-intensive process, you want to make it as efficient as possible because energy is expensive. And so what we had was that we had this formula here for the work or the energy that's required. And the one variable that we were optimizing was P2. And so we ran through our method. We took the derivative of this. It was a little tedious to do just because of the exponents involved, but we finally arrived at an answer of an extrema pressure of P2 of P1 times P3 square root of that point. Okay. So this answer right here was the result of step one. We took the first derivative of the function, we set it equal to 0, and we solved for the value of P2 that satisfied that, and we got this. And so the next step is to characterize this. You know, we only got one extrema, and so we only got one answer by solving that equation. And so, you know, we're kind of at this point kind of hoping and praying that this is a minimum, right? Because if this is a minima, that's good. That means this is the pressure that we should set, and that's you know, it's going to make our process efficient. But if this is a maxima, then this is the pressure that we want to avoid. So we don't want to be in this pressure. So anything but this pressure, right? Let's take second derivative and hope that this is a minimum. So let me pause here for a second. And so, you know, these methods of kind of taking derivatives, you know, sometimes they can be quite time consuming. So in this case, you know, taking the derivative is quite time consuming with how complicated the equation is. Sometimes an easier method, and I do this all the time too, especially if you have a one-dimensional case, is to just kind of plug in. And so what I like to do sometimes is that if I find that the extrema was something like this, well, what I would do is I would plug in values of P2 that are slightly higher than this and slightly lower than this, right? And if those are, you know, higher than the work that's created for this, then it's an extrema, okay? So I'm leave a note. You can also just plug into the function. That's definitely an option. So it's you know, there's no optimization police that will tell you that you need to take a second derivative, right? Sometimes, and a lot of times it is faster to do so, but you know, for situations like this, where we're doing everything kind of based on variables, it's a little bit tougher to kind of plug into the function, unless you have numbers for everything. Okay, so the plug-in method only really works if you have numbers for kind of everything, and you can get kind of definitive numbers. In this case, it wouldn't work out just because we have variables, but you know, sometimes your brain kind of gives you a very intuitive solution, and you know, it's okay to listen to your brain sometimes. All right, but the plugging in won't work here just because we're working purely with just variables here. So let's go ahead and take a second derivative. We're going to take our value of the derivative, which we have up here. And we're going to take the derivative again. Of course, you know, this is again going to be quite time consuming because there's quite a few you know, power rules and exponents that we kind of have to worry about. So, you know, just for the sake of time, you know, I'm not going to go through all that work, but just know that that's kind of what needs to be done. Okay. And so if we do that, and so we're skipping all the work, we get CP T1 times quantity 1 over P1 raised to the K minus 1 over K multiplied by negative K minus 1 K squared P2 raised to the minus 1 over K minus 1 plus P3 raised to the K minus 1 K times minus K minus 1 divided by K minus 2 minus 1 over K P2 raised to the minus 3 minus 1. So of course, you know, to arrive at that result probably would take us half the lecture just to do all the powerful stuff. And so, but if you want to kind of check your work, then you can go ahead and do this. I'm not gonna make you do any derivatives kind of this complicated. Just for this problem, it just kind of ended up like this, just because it was a thermodynamics example with the auditing. You know, for the homeworks and especially for the exam, you know, I'm not gonna make you do something this complicated. That would kind of turn this class into a calculus class, you know, less sort of optimization class. Okay. All right, so we now have our second order derivative, and so what we need to do is we need to evaluate this at the extrema. Okay. So we're gonna plug in P2 is equal to square root P1 times P3. Okay. And we want this to be a minimum. So if we plug that value in there, then what we should hope for is that we should get a positive. Okay. Because if we get a positive number for the second order derivative evaluated at the extrema, then we have a minimum. All right. So unfortunately, you know, I am going to skip the work again. I really want to finish the multivariable stuff today. But you know, you can kind of plug this in and verify. And luckily, we do get a positive number from this. Okay. I know it kind of feels like I'm kind of cheating you guys out of seeing the work, but you know, we gotta move on. But if you plug it in, you know, you'll be able to see that you do get a positive number from this. It makes sense. You know, realistically, it doesn't make sense to have a maxima and then, you know, for everything else to be lower energy than that. So it makes sense that to have a minimum here, but you know, the math kind of supports that as well. Okay. And so that supports this answer of P2 is equal to square root of P1 times P3. This is the minimum, and that is the pressure that we should set the cooling to. Okay. So this right here is the optimal. All right, any questions on this example here? Okay. All right, so let's go ahead and move on then. Let's go ahead and move on to multivariable optimization. So right down in the middle. All right. So, you know, this example kind of closes the chapter on kind of single variable optimization. You know, but most practical optimization problems, optimization studies that you're going to do are going to be multivariable. And in fact, you know, probably most of the really interesting problems are going to be multivariable. Okay. So it's important to know, you know, for, you know, what the kind of the general theme that you're going to see in this class is that, you know, we're going to introduce a method or a group of methods. We'll test it out in 1D first, just so you can kind of see how it works. And then, you know, we'll extend it to multiple variables. Okay, so we're going to do kind of this kind of flip, single variable, multivariable, you know, throughout the class. You know, as it goes. Okay, so let's jump to multivariable optimization. And remember, you know, we're kind of doing the simplest case right now. We're working with no constraints at the moment. we'll start to bring in some constraints on Thursday. Okay. So when I talk about multivariable optimization, what I'm referring to there is that there are going to be multiple design variables. And our objective function will be a function of multiple design variables as well. So for simplicity's sake, just for kind of the examples we're going to do today, I'm going to refer to them as kind of x1, x2, x3. And so on. Technically, you can use these methods for, any number of design variables. It just kind of gets really impractical to do so when you're past one of 3 or 4. Okay. But technically, we can extend this up to x sub n. Okay. And just like the one-dimensional case, we're going to have multiple conditions here, 2 conditions based on the first derivative. The first derivative part, I think, is pretty straightforward. It's the second derivative part that I think is quite different. So let's describe the condition for finding extrema. Conditions for finding the extrema in the multivariable case. Condition 1. So just like our one-dimensional case, our first condition is going to be to take the first derivative of our objective function. The only difference here is that we have to take multiple derivatives, one for each of the design variables in the objective. And since we're in the multivariable case, we are taking, now we have to kind of use the lexicon or the descriptions of kind of multivariable calculus. And so we're taking all the partial first derivatives, okay? And just like we did in the one-dimensional case, we're going to set all of these equal to 0. Okay, take partial f, partial x1, set it equal to 0. F, partial 2. That equals 0. All the way up until partial f, partial xn. And so however many design variables that you have, that's how many first order derivatives that you're going to take. Okay. And so what this is going to give you is that this is going to give you a system of equations. Because now we have multiple variables, we have kind of multiple variables to solve for at once. So it's going to give us a system of equations to solve for the optimal values of each of the design variables. Step 1, there's not too much new to it, right? We're still taking first derivatives, we're still setting them equal to 0. Just the math sometimes takes a bit long because you're solving for multiple variables at once. Okay. All right. Step two. So step two, again, we're gonna take multiple, a higher order derivative. But it gets a bit more complicated in the multivariable case. Okay, so in the one-dimensional case, we took the second order derivative and evaluated the extrema there, okay? For the multivariable case, taking a higher order derivative here, that's, not only are you gonna take kind of the second order derivative of each of the variables, you also have the cross derivative to take into account as well. Okay? And so the way that we can kind of summarize this, because things start to cross over a lot, is we're going to compute something called the Hessian matrix. And so Hessian matrix is basically a matrix of all the second order derivatives. And then, just like in the one-dimensional case, we're going to evaluate the Hessian matrix at each of the extrema that we found in step one. And then depending on the character of the matrix that results, that's going to characterize it as either a minima, a maxima, or a saddle. Okay, so if the Hessian matrix evaluated at the extrema, if that matrix is positive definite, okay, then the extrema that we found is a minima. If the matrix is negative definite, then we have a maxima. I know I'm throwing a lot of terms at you, and so probably this is the first time you've ever heard of the Hessian matrix. Don't worry, we'll go over how to compute it. But I just kind of want to lay out the conditions in all kind of in one clean place, and then we'll go over how to compute all of these things. All right, and so the last case or the last possibility for the Hessian matrix is that it is what we call semi-definite. If it's semi-definite, then what we have is a saddle point, so neither a max nor a min. Okay. So this step, computationally is going to look different than the one-dimensional case, just because first of all, you have to compute a lot more second order derivatives. And you have to do a little bit of kind of matrix algebra to kind of get to result. But once we do a couple of examples, I think you'll be able to. Okay. So next thing I want to show you is how to actually compute the Hessian and determine if it's positive, negative, definite. But are there any kind of just questions on just these two conditions? Okay, all right, so let's go over how to compute the Hessian. Okay. So like I said, the Hessian is a matrix, okay? It's a square matrix. Right, and so square matrix meaning that it has the same number of rows and same number of columns, where the dimension of the matrix is determined by how many design variables that you have. And so if you have two design variables, then your Hessian is going to be a 2 by 2. If you have three design variables, then you have a 3 by 3. Okay, and so on and so forth. And so the way to compute it, so oftentimes we use the symbol H or capital H for the Hessian. Okay. It's the second order partial derivative of f with respect to the design variables. But of course, the exact derivative that we compute is going to depend on the combination of, which design variables that we choose. Okay? So I'm using index notation here. So, it is, partial squared f over partial xi partial xj, okay? Where I and j here refer to the row and column of the matrix. The notation gets a little bit kind of, a little bit kind of, I would say a little bit opaque, if I kept up the index notation. So I think the easier thing would be to kind of show you kind of the two-dimensional example. So with two design variables, what the Hessian would look like, and then we'll go with the three-dimensional example. And then from there, I think you guys will catch on to the pattern. Okay. Okay, so this is for two design variables. So like I mentioned, for two design variables, our Hessian is going to be a 2 by 2 matrix. And so for the first row and the first column, we're going to have the partial squared f, partial x1, partial x1. So that's just partial squared f, x1 squared. Okay. First row, first column. For the first row, second column, it's going to be partial squared f. This is going to be a cross derivative. Partial squared f, partial x1, partial x2. So to take a cross derivative, you would first take the derivative of our objective function with respect to x1, then you take the result of that and you take the derivative with respect to x2. Okay, so you kind of swap the derivatives when you go from one to the other. For the second row, first column, we have partial squared f, partial x2, partial x1. And then finally, in the bottom right, partial squared f, partial x2 with that second row, second column. So we're taking the derivative with respect to x2 plus. Okay. Let's compute the Hessian, or let's see what it looks like for three-dimensional case. Then I think from there, you'll it's pretty easy to pick up on the pattern. And I'm not going to ask you to do anything beyond 3 dimensions. So 3 design variables. This one's significantly bigger. It's a 3x3 matrix, so we have 9 entries to write here. Give myself a little bit more room here. Okay. So in the top left, it's the first row, the first column, so that's partial squared f. Partial x1 squared. Okay, first row, second column, we have partial squared f. X1, partial x2. And first row, third column, partial squared f, partial x1, partial x. Okay.
And this is mostly just conceptual, right? So
Yes.
it's like most of what we're gonna be doing. It's gonna be.
Yes, yeah. Well, these methods we're not doing in MATLAB because these are the classical methods, but yeah, these are all kind of conceptual. We'll do an example kind of showing this a bit later too. All right, second row. The second row, first column, partial squared f, partial x2, partial x1. Second row, second column. Partial squared f, partial x2 squared. Second row, third column, we have partial squared f, partial x2, partial x3. Just gonna finish this up. Just kind of following the same pattern. So, I'll be the first to tell you that, this does get pretty tedious, especially for kind of higher order problems. And so you can imagine if you get up to four dimensions, 4 design variables, you have a 16 entry Hessian matrix. So that's 16 different derivatives that you have to compute. Well, it's not exactly 16 because, this matrix is symmetric, but it is still a lot. And then 5 dimensions, you have a 5 by 5, 6 dimensions, 6 by 6. And so, it gets very quickly out of hand. And this is not even the worst part. The worst part is actually determining if it's positive, definite, negative, definite. So. Any questions on this so far? Crashing a little bit. The sugar is leaving. Right. Okay, so the next step is to determine whether this matrix is positive, definite, negative, definite, or. Okay. Have you guys heard those terms before? Have through previous math classes kind of mentioned those at all? Probably not. It's yeah. I didn't learn about positive definiteness until grad school. Okay. So to determine whether a matrix is positive definite or negative definite, there's lots of ways to do it. What I'm going to show you is probably the simplest way. Okay. So to determine if a matrix is positive, negative, or semi-definite, what we need to do is we need to check the determinants of the principal submatrices. All right, so what are the principal submatrices? So the principal submatrices are, basically all the square matrices that you can make from this matrix, starting from the top left corner. So what do I mean by that? So that's kind of a fancy way of just saying, go from the top left corner. Your first principal submatrix is a 1 by 1 matrix that's just literally just the top left entry. Okay. Your second principal submatrix is a 2 by 2 matrix. That's the top left 4 elements. And then your last principal submatrix is just going to be all of it. Let me kind of show you. So to come back up to this 3 by 3 example, the first principal submatrix, kind of unfair to call it a submatrix, one entry. So this is the first submatrix. The first principal submatrix is literally just the top left entry there. Okay. The second principal submatrix is that we're going to again start from the top left corner, and then we're going to encompass that 2 by 2 matrix up there. So that's the second principal submatrix. And then the third principal submatrix is going to be the entire. Okay. And so what you're going to want to do is you want to take the determinants of all of these submatrices. Okay? And then based on the signs of those determinants, that's going to tell you whether the matrix is positive definite or negative definite or semi-definite. Okay, so if all the determinants are positive, if all the determinants are positive, then our matrix is positive definite. And just to kind of remind you, if you have a positive definite Hessian matrix, that means we have a minimum. Okay. So that's the simplest case, and so you kind of pray for that all the time, and you get a positive number all the time. That's the simplest one. Okay. The condition for negative definite is a little bit complicated. So yeah. It would be great if this was just, if they were all negative, they'd be negative definite, but math is not that so simple. It's not very nice sometimes. So if the first determinant, so the basically the top left entry of the matrix is negative. So that's the first condition. You have to start with a negative number. Okay. And then each of the subsequent determinants, if they alternate in sign, so if they go negative, positive, negative, positive. So, you're looking for, you're basically looking to see if the top left entry is negative. And then if all the other determinants, go positive, negative, then what we have is a negative definite matrix. And so luckily the last condition is easy. And so if neither of these cases are true, and so if you don't have all positive determinants, or if you don't have this alternating sign, then your matrix is semi-definite. That was a lot of math, so there was a lot of kind of calculus and in terms in kind of a short period of time. But don't worry, I have a couple of examples to kind of illustrate this for you. So I know we'll get through one example today for sure. If we don't finish the second example, then we'll finish it up on Thursday. I definitely want to make sure that you guys get plenty of examples with this, because I think it's probably your guys' first time computing a Hessian and taking determinants and finding positive, negative, definite. Any questions on this before we jump into an example? Okay, all right, so let's do an example. So what's interesting about this example that we're going to do, we're jumping right into a physical example, by the way. We're not going to do any just kind of abstract math one. What's interesting about this example is that it's not strictly an optimization problem. It's technically a mechanics problem, but you can solve it using an optimization framework. Okay, so let's say that we have two carts that are supported by 3 springs. Maybe I should say 2 carts constrained by 3 springs. Something like this. Wall that's fixed on the left side. We have 1 spring that's up here. Okay. We'll call the first spring K1, and so K1 is going to be the spring constant for that first spring. Okay. That's going to attach to a cart right here. On the bottom here, we're going to have another spring. We'll call that spring K2. That's going to attach to a smaller part. That smaller part is going to attach to the bigger part using another spring. We'll call that K3. So 3 springs, 2 carts, and we want to know what's going to happen. So what we're going to do to this system is that we're going to pull on it. And so we're going to apply a tensile force P. And so we're going to apply a force P. We're going to pull this entire structure to the right. Okay. This entire mechanism here is going to go to the right. but the amount of movement is going to be constrained by the springs. But then each each cart is going to move independent. Okay, so let's call the smaller cart 1, just because it's on the left. And we'll call the bigger cart 2. Okay. And so after applying the force P, cart 1 will move to the right x1. And cart 2 is going to move to the right by an amount x2. After applying load P. So after applying the load P, the carts are going to displace by the amounts x1, x2. Okay. All right. So let's assume for this problem that we know all of the spring constants. So K1, K2, K3 are known. So we're not going to optimize on those. Okay. We're going to assume that we know the load P as well. Let's assume K1, K2, K3, and P are known. So those are fixed variables or fixed parameters in our system that we don't need to include in the optimization. Okay. And so what we want to find or compute is we want to compute the displacements x1 and x2. So that's the problem that we're going to solve in this one. Okay. Technically not an optimization problem, and technically you can solve this, in a lot of different ways. For those of you in my finite element class, we could actually solve this with finite elements pretty easily. But we're going to solve it using optimization because this is an optimization class. All right, any questions on just the problem setup, just the variables and the geometry? Okay. All right. So how can we solve this with optimization? It doesn't seem like an optimization problem at all. So whenever you have essentially, we're going to have this situation in static equilibrium, right? The thing with static equilibrium is that whatever configuration or shape or deformation state that a structure or system settles in, that's always the state with the lowest potential energy. This is true for all kind of static situations. Okay, any kind of static situations that involve some deformation or displacement, whatever it settles down into is whatever the state with the lowest potential energy is. Okay, and so what we can do is that if we can form our objective function based on the potential energy. And so if we can come up with a function or an equation that that kind of tells us the total potential energy of the system, of course that's going to incorporate the spring constants, that's going to incorporate the force, It's gonna incorporate the displacements as well, okay? And so if we can come up with that function, then we can solve this like an optimization problem, because what we want to do, if we can get that function for potential energy, all we have to do is find the minimum, right? So we can use our optimization methods to find the minimum of that potential energy, then that's going to tell us the static and configuration. Okay. So that's going to be our strategy, right? So we're going to compute the potential energy or come up with an equation for it, and then minimize it using derivatives and Hessians and all that. Okay. So let's recall, before we write out the potential energy of the whole system, let's recall the potential energy function for a spring. I'm going to use the symbol capital U to determine or to kind of denote potential energy. And so the potential energy of a spring, right? So when I talk about potential energy, this is the energy that's stored in the spring as we stretch it or as we compress it, okay? Because, if you think of a spring, right, it takes energy or work for you to stretch it, right? And so all that work that you're doing to kind of stretch the spring, that's going to be stored as, mechanical potential energy within that spring. And so, of course, the amount of potential energy that's stored in there is going to depend on the deformation, and it's also going to depend on the spring constant. So the formula we have here is 1/2 K x squared, where that x is going to be how much the spring is stretched. So what we're going to do is we're going to apply this equation to all three springs in our system, and then add them all up, and then that's going to be the potential energy of our system. Okay, let's go ahead and apply that. Okay, so the potential energy of the entire system, we're going to go one by one, right? So we're going to go to spring 1 first. So spring 1 has a spring constant K1. The amount is going to be stretched. So let's go back up to our figure. Right. So K1 is our spring that's up top, that's only attached to cart 2, right? So spring 1 doesn't attach to cart 1 at all. And so the amount that it's going to stretch is just however much cart 2 is going to deform. So this potential energy is going to be 1/2 K1 times x2 squared. This right here is spring 1. Let's go ahead and write the potential energy for spring 2. So spring 2 is going to be 1/2 K2. We come back up to the figure up here. Spring 2 is attached to the wall, so it's the one in the bottom left there. It's attached to the wall and it's attached to cart 1. Okay. So the amount that spring 2 is going to stretch is going to be just however much cart 1 moves to the right. This would be 1/2 K2 x1 squared. And we have spring 3, we have 1/2 K3. Spring 3 is a little bit unique because it's the only spring that's attached to both carts, okay? So the amount that it's going to be stretched is actually going to be the difference between x2 and x1, okay? So it's going to be 1/2 K3 quantity x2 minus x1 squared. We come back up to the figure up here. We can see that K3 is between cart 1 and cart 2, right? So both carts are moving to the right? So, so when we pull on P, then, cart 1 and cart 2 moves to the right. So, the amount that K3 is going to stretch is going to be however much K2 displaces minus however much K1 displaces. So that's going to be the total stretch of speed. Okay. And then one last thing we have to add to our potential energy function here is the amount of work done by the force P. But that's also contributing to the energy of the system. We have a minus P times x2 because that's the amount of force. That's a force multiplied by a distance. So that's the amount of work that P2 is doing. All right, any questions on how we form this equation here? Okay. All right, so we have our objective function, we have our design variables. They're not really design variables in this case because we're not designing anything, but there are, so just going to use the same terminology. Okay. So what we want to do is we basically want to find the optimal values for x1 and x2 that minimize this equation. Okay, so let's go ahead and start applying our classical method. Okay. So first, let's start with the derivatives. Let's take our first partial derivatives, and so we're going to take partial u. So x1. Right, so remember when you're taking partial derivatives, the other variable is going to be there, but we treat the other variable as a constant. Okay. And so that first term there, we have 1/2 k1 times x2 squared. For all intents and purposes, when we're taking the derivative with respect to x1, that term is just going to go away. So I'm going to go term by term here. So taking the derivative with respect to x1 on that first term is just going to be 0. For the second term here, we have one derivative of 1/2 k2 x1 squared. And so by power rule, that 2 is going to come out in front. So we have positive k2 x1. Then we have the derivative of the next term. Okay, so the next term is 1/2 k3 times x2 minus x1 squared. So we can do a little bit of chain rule here. And so the derivative of the, we're taking the derivative of that inner part. We're taking the derivative of x2 minus x1, which is a -1. Then we're going to take a derivative of the outer part. So we're going to take a derivative of 1/2 k3 times quantity, x2 minus x1 squared. So that's minus k3, x2 minus x1. You could of course FOIL that out. So if you're kind of uncomfortable with the chain rule, you can FOIL out that quadratic term and take the derivatives kind of term by term if you want. Okay. And then we have the derivative of the last term, the px2. Again, we don't have x1 in this term, just like the first one, and so we're just going to end up with 0. And so we're going to set all of this equal to 0. Okay. So let's do the same thing, but let's take the derivative of our potential energy with respect to x2. So derivative of the first term, we have derivative of 1/2 k1 x2 squared. So when we take the derivative with respect to x2, we get a k1 x2. Okay. We take derivative of the second term, we take the derivative of spring 2. We don't have any x2 in there, so that's just going to be a 0. We take the derivative of the third term. Once again, we're going to apply chain rule. We get k3 x2 minus x1. We have a positive there because, you know, when we take derivative of the inner part, it's x2 minus x1. So derivative of x2 minus x1 is positive 1. Okay. And then finally, we have the derivative of minus px2. And so that just gets rid of the x2, and we just end up with the minus p. Okay. And then we're going to set all that equal to 0. Okay. So what we have here is we have an equation of two equations and two unknowns. X1 and X2. And so, you know, there's really, you know, no kind of easy way around this. And so now we need to do the algebra to solve for X1, X2 from this system. Any questions on how we got here? Okay. All right, so we can go ahead and solve this. So I know there's lots of different ways to solve a system of two equations and two unknowns. I usually like to do it by just direct substitution. So I'm going to solve the first equation first. Okay. So let's solve the first equation for x2. Of course, you know, we're not going to get an answer from this. It's going to be a function of x2. That's a function of x1. Okay. And so to solve that first equation for x2, it's pretty straightforward. So we have k2 x1 minus k3. Can you go ahead and distribute that k3? You have k2 x1 minus k3 x2 plus k3 x1 is equal to 0. Okay. I'm going to move this term, the k3 x2, over to the other side. It's the only term with x2. So on the left-hand side, we have k2 x1 plus k3 x1 equal to k3 x2. I'm going to divide both sides by k3. That's going to get rid of the k3 on the other side. And so what we get from this is x2 is equal to, I'm going to factor out the k1 as well, or x1, excuse me. x1 times quantity, k2 plus k3 over k. Okay. Let's go ahead and plug this into the second equation. So basically, everywhere we see x2 in the second equation, we're going to plug in this. Okay. The first up, we have k1 times x2. k1 times this, x1, k2 plus k3. That's our first term there. Okay, that k1 x2. I'm going to skip over the 0. Second term that we have is k3 plus k3 quantity x2. So let's go ahead and plug in for x2, x1 times k2 plus k3 over k3 minus x1 minus p It's all equal to 0. A little tedious, there's a lot of K's around here, but now what we have here is just a single equation for a single unknown. So we can solve this one for x1. Okay. So to solve for x1 here is just algebra at this point. It is tedious algebra, but let's just kind of work through it. Okay, so first thing I'm going to do is I'm going to distribute the k1s. Okay. All the k's is just to isolate each term kind of individually. Let's start by distributing. Okay. So if we distribute, then what we have here is k1, x1, k2 plus k3, over k3, plus for the second term here, we're fortunate in that the k3 will cancel out. So this k3 is going to cancel out with this k3. Plus x1 k2 plus x1 k3 minus k3 x1 minus p 0. If you look at the third and fourth terms there, you can see that they're exactly the same. They're just kind of swapped, right? And so we have an x1 k3 here, k3 x1 here. We have a minus sign in between them. So these two terms are just going to cancel each other out. Okay. Always satisfying when that happens. Okay. I'm going to take this p. I'm going to move it to the other side of the equation because I know that that's the only term there that doesn't have x1. And so that's going to be kind of our other side. Okay. And then I'm going to finish distributing for this last term here. Okay, so this last term here, a little bit complicated. And so we have k3 or k1 times k2 over k3 x1 plus we have a k1 k3 over k3 x1. Of course, the k3 over k3 is going to cancel each other out, so that's going to be just 1 there. Okay. Plus k2 x1. All this is equal to p. So technically from here, you can factor out the x1, right? So every term on the left-hand side has an x1 and you just divide the entire thing by that factor. That's going to solve for x1. I'm going to do an extra step here just to simplify this. So I'm going to multiply this entire thing by k3. Just to kind of knock that k3 out of that denominator on the left-hand side. And so doing so, we have k1, k2, x1 plus k1, k3, x1 plus k2, k3, x1 equal to pk3. It's going to make it a little bit simpler to solve for x2 later on too. Okay. All right. So now that we have it in this state, there's kind of no messy fractions. What I'm gonna do is I'm gonna factor x1 out of each of these terms. And then we're gonna divide by whatever's left. Okay, and so by doing so, we finally get our solution for x1. So x1 is gonna be pk3 divided by k1, k2 plus k1, k3 plus k2, k3. And then very last thing, you know, let's kind of finish this up. Let's plug this in and solve for x2. So remember our formula for x2 that was given up here. So x2 is equal to x1 times k2 plus k3 over k3. Okay. And so if you'll notice the form that we have for x1 here, we have a k3 up top. Okay. And so that k3 up top is going to cancel out with the k3 on the bottom. And so we get x2 is equal to p times quantity k2 plus k3 all over. Same denominators, k1, k2 plus k1, k3 plus k2, k3. Okay. All right, so when we come back on Thursday, we didn't have time to do the Hessian today, so on Thursday, we're gonna pick up this example, we're gonna compute the Hessian, and just like we did with the example at the beginning today, we're gonna pray that this is a minimum. I'll give you a spoiler, it is a minimum, so we'll kind of demonstrate how that's found on Google. All right, so thank you guys for coming in today. I apologize for going over a little bit of time. So hope you guys have a good rest of your day, and I will see you on Thursday. Sure. What's that?
Separate.
I just waved at it. I went, ooh, where did your friend get it? I was sweet for you know where your friend got 0.5. No, which one? The number that.
Yeah. Okay, what did you say?
No, like basically, sat next to each other, and like. For me, times before like Facebook, you make little like a super simple chart like.
Okay, so
Yes, number of guesses and number you picks, and then like maybe like how many guesses he picks, yeah.
So this plot looks good, right? Actually,
Number 4.
So
I had
X value from 0 to
I
5.
had to
So you just make a plot.
pretty much have to find it. What I'm saying.
And Y value from 3 and.
You could try to plot it not in that line, but maybe it was like a 3D.
So if you look at the, so what you have right here, that's.
Once you just set.
So the
Once you set y equal to a certain number,
Yeah.
while x1 and x2 are changing, but x1 and x2 are only changing between.
So I think one kind of simple way. You can
So it's kind of weird,
save
like,
this as a unity
you can't.
and then open up in peaks and then draw a box. Yeah, deal. Yeah,
Sounds good.
yeah, that's probably the easy. That's what I did math basically.
All right.
Did you get it on there?
That's not happening. I went back to sleep.
Yeah. Maybe do that in Excel, I think.
And then.
It goes 0 to 10.
I forgot how to use Excel. There's a way that you can put multiple lines on the same line.
So just like.
Oh,
Yeah, I think yeah, I think if you Google it, if you Google, I don't know what, how to plot multiple lines in Excel. You should copy off that. Yeah.
My question is the same about.
Yes,
No problem.
Oh, Christine, hi, do you wanna go to the library? Sure.
I think that's what people are. That's fine. I think that.
We can learn. Oh, super.
I think that's.
I like that speaking.
Every single. Oh, thank you.
It's
I'm gonna start reading it next week. I'm sorry, I'm weird. No.
Yeah, somewhere kind of inside. About 7, but,
Yeah.
I think it's on like page 6. So.
I was walking the clock and all of a sudden.
Oh, okay.
And I was
That's cool.
You going home right now?
Going to birthday dinner.
Birthday.
It's kind of relative. It's like
I'm just trying to figure it out.
Yeah, but. So when you say, oh, you're getting further. Yep. And then your next get. 16, you know, or
Yeah.
maybe on to it.
We haven't even used that.
Yeah, it's just. Did you, Harvey, you're probably gonna have wanted guesses because it takes a while just with warmer.
I do it.
Exactly.
It just looks like kinematic, it looks like vibrations right now, really. It's kind of like I mean, there's the find min and the maximus.
Yeah.
Oh, then yeah, that's just.
Sorry. This is like an X and a Y, sorry.
Oh, okay.
I was just like.
Yeah, you can do X and Y is fine too.
Thank you, I saw it now.
Chilling. Did you get it?
You guys are wearing green.
You
Oh
are.
my god.
Oh my God, we're all wearing. You take it.